Hello and welcome to the Outer Limits of Reasoning, where we're talking about what can and cannot be known. So this is from this Outer Limits of Reason. We're up to chapter 5. Okay, so in this class, the first part of the class was a little bit more philosophical, languages, and a little bit of set theory. The second half of the class is mostly about computers. So we're going to spend a long time on chapter 5, and chapter 6 is also about computers. So let me just tell you what chapter 5 and chapter 6 is about. Chapter 5 is what computers can do, but it takes them a long time to do. Okay, we're going to see there are going to be some very simple problems that I'm going to explain to you that computers just take centuries to solve. It would take a very, very long time to solve. In contrast, chapter 6 is computer problems that a computer cannot solve. Not that it would take a long time to solve, they just can't do it. Okay? But we're going to spend a lot of time on chapter 5, and we're gonna put in a long time. Okay, great. So let me start off with a few things. We're going to start off in the beginning of chapter 5, just to get the lingo of what computers are all about. We're going to start off talking about easy problems that computers can solve in a short amount of time. And with this, we're going to learn a lot about computers and things like that. We're going to learn how computers work and also how we measure how computers work, or how well they work. Okay, I'm not going past this line. Okay, so let's begin. Okay, so computers have changed our world, and they can do a lot of amazing things, but we're going to talk about some easy things they can do. So the first thing they can do is addition. Okay, that's a pretty simple thing. Every computer can do it. Okay, again, we're just trying to talk about easy things before we get to the hard part. So let's just see how a computer would add numbers, or let's talk about how many operations it takes to add numbers. So if I give you a bunch of numbers like 5, 3, 8, 7, 6, plus 2, 4, 1, 9, 5, okay, a computer can add them as follows. Here's two 5-digit numbers. I want to see how long you can add them. Not how long, but how many little operations does it take? Okay, and the answer is 6 plus 5 is 11, carry the 1. This is 17, carry the 1. This is 10, carry the 1. This is 1 plus 3 is 4, plus 4 is 8. 5 plus 2 is 7. So I was able to do that with about 5 additions. By that I mean I had to do this addition, this addition, this addition, this addition, this addition. Sometimes I had to worry about the carry digit, but that was a little bit extra thing. We don't have to worry about that. So we can do these things with about 5 additions. The red light's on. Okay, now, is the red light on? Don't shut it. Is it on? Okay, good. Thank you. Okay. If I gave you a 9-digit number, then you have to do about 9 little digits. In particular, if I had 2 n-digit numbers, I would have to do n little additions. Okay, so that's a pretty easy thing. In contrast to addition, multiplication is a little bit more complicated. And that's the reason why addition we teach in 2nd grade or in 3rd grade, and multiplication of many digit numbers we teach in 3rd, 4th, 5th grade. Okay? So how would we do this for multiplication? Well, we can erase this, and we can say, okay, how do you do for multiplication? You take 2 5-digit numbers, how do you do it for multiplication? Well, you multiply this times this. 5 times 6 is 30, carry 5 times 7 is 35, carry the 38. 7 plus 3, carry the 8. 5 plus 8 is 40, carry the 3, so it's 43. Okay, and then you do this and you put in this one. Then you stop worrying about the 9. 9 times 6 is 54. Okay, you put the 5 there. 9 times 7 is 60 whatever. Okay, then you just do the 1. The 1 I can do with ease. 6, 7, 8, 3, 5. And the 4, then you worry about the 4. Okay, now, how many operations does this demand? How many little operations do you have to do? Notice what you're doing. For every one of the bottom ones, you have to multiply the top one. So it's this times this, and this times this, and this times this, and this times this, and this times this. And then you do this times this, and this times this, and this times this, and this times this, and this times this. Every one of the bottom numbers has to be multiplied by every one of the top numbers. Okay, so you have 2 5-digit numbers. How many multiplications do you have to do? Forget about the additions afterwards. You have to add these all up. How many multiplications do you have to do? And the answer is, well, if every single one of the bottom digits has to multiply against every single one of the top digits, so then you have 5 times 5 multiplications, okay, which is 25. Great. How about if there was 8 digits? I had 2 8-digit numbers. How many multiplications would you have to do? And the answer would be 8 times 8, which is 64. Okay, great. Now, let's talk in general. If I give you n digits, where n is some number, and I ask you how many multiplications does it take, okay, you have to do n times n, or n squared multiplications. Okay? So this is a reason why addition is easier than multiplication, because addition is what's called an n operation. It takes an n amount of time to do things. As opposed to that, multiplication is a little bit harder because you have to do n squared operations. Okay, and what we're going to see is we're going to describe how complicated problems are by how many operations they have to do. And the intuition is as follows. If the computer can do if it's a few operations like additions, the computer can do it quickly. N squared, the computer will take a little bit longer. Just like human beings. To add numbers is a short amount of time, just to multiply numbers takes a little bit longer. Okay? Okay. So these are 2 simple operations. Okay, great. Let's talk about something else. Okay? Let's talk about something else. Let's talk about another simple task that computers are very good at, searching. Okay, searching. Okay, so I'm looking for somebody in this class. Now, obviously I can say, Joe Blow, raise your hand. He'll raise his hand and I'll find him very easily. But let's say I'm looking for something in this class, somebody in this class, and I don't know. And so I want to do it with little questions. I want to ask every single person in this class, are you Joe Blow? If they say yes, I stop. If they're not, I go to the next one. Are you Joe Blow? Are you Joe Blow? Are you Joe Blow? Are you Joe Blow? And go through the entire class till I come to the end of the class. Now, there are 40 students in this class. What's the worst possible thing that can happen? Okay? The worst possible thing that can happen is I can start from the beginning of the class, go through each person, ask them, are you Joe Blow? Are you Joe Blow? Are you Joe Blow? Are you Joe Blow? Okay? And the worst thing that could happen is I'll get to the last person and I'll ask him, are you Joe Blow? Now, he could be Joe Blow, and then that's very nice. I asked 40 people and I got it. Or Joe Blow could not be here. Okay? And he'll say no, but again, I have to ask 40 people. Okay? And we're always interested in this question. What is the worst case scenario? Okay? What's the worst case scenario? We want to know what's the worst thing that can happen. You see, okay, so let's go through, by the way, what's the best case scenario? Okay, I'm looking for someone, what's the best possible thing that can happen? The best possible thing that can happen is I can ask the first person, are you Joe Blow? And they say yes. Finish. Problem solved. Okay, that's the best. On average, so we have the, what's on the average, typical thing that would happen? Not the best, not the worst, but the average case is, I would ask about 20 people, 25 people, and Joe Blow would be somewhere in the middle of the room. Okay? Okay, so I just want to do this, instead of looking for people, I want to look for a particular number. So let's just talk about these numbers. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You know what? Let's put them all up. Okay. Okay, great. Okay, so let's say I'm looking for the number 22. Okay, so I start here and I say, that's not 22, that's not 22, that's not 22, that's not 22. Okay, I find 22, I'm happy. Okay? In this case, how many questions did I ask? How many little questions did I ask? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I stopped at 10 because I found 22. Great. Now, let's say I'm looking for number 23, not 22, 23. Look what will happen. Are you 20? Now, again, human beings can see this very quickly, but really human beings are cheating because human beings are looking through it just very quickly, each one. But if you're looking for 23, this is not, are you 23, are you 23, are you 23, are you 23, 23 is not found. Okay, so in that case, I have 16 cards here, and I have to ask 16 questions. Okay, now this is very good. This is very good. Okay, so let's just go through what's the worst case. The worst case is if I have 16 cards, I'll ask 16 questions. For example, if I'm looking for the number 39, then I would have to ask 16 questions until I count to 39. Or, if I'm looking for, let's say, 21, I'd have to go through the whole thing and see that 21 is not on my list. 21 is not on my list, so then I would have to ask 16 questions. Best case scenario, I ask one question. For example, 32, are you on the list? Oh, yeah, he is. I asked one question. Okay? And another question another way we can measure is the average case. What's the average case? And again, the average case is around halfway through. In other words, sometimes I'll ask a few questions, sometimes I'll ask many questions, but on the average I'll ask about 8 or 9 questions. So the average is about 8. Okay? Now, this is for 16 cards. What happens if I had 58 cards, or if I have, let's do 100 cards, or if I have 100 students in this room, okay? What's the worst case scenario? I go through all 100 students, and I see that the last one is there, or the student is not in the class. What's the best case? The first, okay? Et cetera, et cetera. Okay, so in general, the worst case is, for n cards, is n. The best case is 1. And the average case is, you're going to have to ask about half of them, yes, no question. So that's n over 2. That's half of them. Okay? So that's interesting. Now, there's something else we can do here. Okay? It goes as follows. Let's imagine for a second you're looking at the, boys and girls, there used to be something called a Brooklyn telephone book. Okay? A Brooklyn telephone book had phone numbers for 4 million people. Okay, so it was a very large thing. Now, if you're looking for somebody's number in the Brooklyn telephone book, you have a problem. Okay, you're not going to start looking at them from the beginning to the second to the third to the fourth to the fifth because there's 4 million people. Let's say you're looking for Mr. Sherman in the telephone book. What do? You don't just start from AAA plumbing supply. You keep on going. You don't do that. What you do is you take the Brooklyn telephone book, imagine this is the Brooklyn telephone book, and you split it in half, okay? And you see, let's say, this is Miller. Should I look I'm looking for Sherman. Should I look in this side or should I look in this side? Okay? And so S, Sherman, comes after Miller, so you look over here, and you split it up in half. You look on this side, not on this side. Okay, you take this side, you split it in half, okay, and you get to the U letter, okay, somebody, Ehrman, okay, okay, now you're looking for Sherman, so what do? You know it's not in this part. Should you look in this part or this part? Again, this is M, this is U. Should you look at this part or this part? And the answer is Sherman is between M and U. It's S. And so you go here and you split it again. And you keep on splitting over and over and over until you find what you're doing. Now, that's the way you look at something in the Brooklyn Telephone Book. Okay? Let me show you in terms of cards. The Brooklyn Telephone Book is very interesting, but the cards are, the names are in order, so you can do that. So let's do it. Okay? Let's just put them in order for a second. Okay. 32. Hold on, don't move. Press stop. Okay, so here we have the ordered things, okay? So let's say, again, I'm looking for the number 33. So what I would do is, I would try halfway through, I would try here 35. And I'm looking for 33, so I have to go this way, okay? So half of this way is 24, okay? Now, so I look at 35, I say, no, the number I'm looking is 33 there, okay? Again, I'm looking at it as a computer, which can look at the numbers one at a time. And I say, no, it's on this side, so I go to 24. Okay, great. Is it on this side of 24 or that side of 24? Well, 33 is more than 24, so I go to this side. So we look somewhere in between here, okay? In between here and here is 33. And I see, oh, 33, that's the one. Okay? Okay. This is called a binary search. The binary search algorithm. A binary is a bicycle, 2. You take your list and you split it in 2. Okay? A binary search algorithm. And you keep on splitting and splitting and splitting. Let's see what else can happen. By the way, let's say I look for 31. Let's see what would happen if I look for 31. Okay? So I started looking halfway through. Okay? And I say, no, it's less than 35. Okay? So I split halfway, I get to 24. 31 is more than that. So we go to 33. 31 is less than that. So I look between here and here, I get to 32. 32 is more, so I try going here. Buzz, there's nothing there. 31 is not on this list. Okay? Okay, great. Okay, let's try something else. I'm looking for 42. So I go here, 35, 42 is more, so we try here, 42 is less than 45, so we go here, and we bounce it around. Okay, now, these two sorting methods, there's two ways of sorting things. One is called brute force, searching. There's two ways of searching. One is called brute force searching. That means just try every single one. Brute force searching. Okay? And what is called binary search. Binary search is a little bit more complicated, but it's a lot quicker. Okay? Okay, so let's just remember, in the worst case scenario for brute force searching, you need n possibilities. But in a binary search, you have the amount of times you can chop a number in 2. Okay? So again, you have 16 cards, you can chop them. You get 8 cards on each side. Okay? Then you can chop it again. You get 4 cards on each side. And you can chop it again. You get 2 cards on each side, etc., etc. Okay? So the amount of times you can chop it. The amount of times you can chop it is called the number of the logarithm of n. So we have to do with logs. Okay, great. So we need a review. I know you've seen logarithms before, but we need a little review of it. Okay, so let's just remember a little bit about logs. Okay, I'm going to take 1,000 and see how many times I can split it in half. Okay, and it's not going to go so easy. So 1,000, I'm going to split that in half. I'm going to get 500. I'm going to split that in half. I'm going to get 250. I'm going to split that in half. I'm going to get 125. I'm going to split that in half. What's 125 divided by 2? Okay, I'm going to get 60. 60 is 120. I'm going to get 62. Okay, now that's not really true. It's 62.5. It was 62.5. It was 120. Okay, but I like 62. Anyways, but there's a little bit of squiggle here because I don't want to get into decimal numbers. Okay, 62, 31. I'm going to go to, instead of 15, I'm going to go to 16, 8, 6, 8, 4, 2, 1. Okay, question. How many times were we able to split the numbers? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so what we write is log of 1,000, okay, but we squiggled around here. We fudged it around there. So we're going to write log of 1,000 is about 10. Okay. Let's just, while we're here, we had 16 cards over here. How many times can we split 16? 1, 2, 3, 4. Log of 16 is equal to 4. Okay? Which means, in the worst case scenario, we're going to ask 4 questions. Okay. Now, in the worst case scenario, for the brute force search, we had to ask 16 questions. We'd rather ask 4 questions than 16 questions. Okay, great. Now, let's just do a big logarithms. Let's see how many times we have to do if we went through the 4 million names in the Brooklyn telephone book, how many times we'd have to split those in half. So it goes as follows. It's 4 million, 2 million, 1 million, 500,000, 250,000, 125,000, 62,000, I don't want to get into the little hundreds, okay? 31,000, okay? Let's say 30, let's just write this as, think of that as 32,000, so then we have 16,000, 8,000, 4,000, 2,000, 1,000, okay? And we know how many times we have to split 1,000 to get to, all the way down to 1, okay? So let's do that again, just in case. That's 500, 250, 125, we're going to do the same trick as we did before. 62, 31, 16, 8, 4, 2, 1. Okay? Now let's count how many we do that. Okay? So we have to split it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. 22 times. So what we say is as follows. The logarithm of 4 million equals 22. Okay. And let's go back to the Brooklyn telephone book. I'd rather do 22 checks than 4 million. For example, let's imagine I'm looking for ZZ Top in the Brooklyn telephone book. Okay? I'm looking for ZZ Top in the Brooklyn telephone book. If I was to do a brute force search Okay? If I was to do a brute force search, I'd have to go through all 4 million numbers. Don't want to do that. Okay? Let's see. It's not AAA plumbing supply. It's not AAA zebra. It's not da-da-da-da. Go through all the A's, all the B's, all the C's. Don't want to do that. In contrast, what I do want to do is do the binary search. I have to check 22 numbers. 22 is a lot smaller than N. So this algorithm is a lot quicker than this one. Okay. But I can't. Okay, you are responsible to know a little bit about logarithms, so that's fine. Okay, but the main thing is, why should I ever do this algorithm? Why should I ever do this algorithm when I can do this algorithm? Obviously, this algorithm is much better than this algorithm. It takes a shorter amount of time. And the answer is, not all the time is your data, is your input so organized like this. I had to sort them first. Now I can do the binary search. You can't do the binary search with students sitting in a class because they don't sit in any particular order. So I can't say, okay, I'm looking for Mr. Sherman. Should I go to this side of the class or this side of the class? When you're in 3rd grade and I put you in alphabetical order, then maybe you can do it, but not really here. Okay? Let me just explain to you a case where this is important. Let's just say what we're saying again. What we're saying is you can do the brute force algorithm in any type of data, but you can do the binary search algorithm only when the data is totally sorted. When it's totally sorted, you can do it. Okay? Okay. Let me just give you an example of when this shows up. You ready? You go to a party, okay, and miraculously you get a girl to give you her number. Great, you have her phone number, okay, but she didn't write her name on it. The next morning you wake up, you have the girl's phone number, you don't have her name. Big problem, okay? So what do? See, you can't just call her and say, oh, I forgot your name. You're not going to get anywhere. So what you have to do is as follows, is you have to take your phone number that she gave you on a piece of paper, take the Brooklyn telephone book, and you have to search through it. But here, Brooklyn telephone book is sorted by name, not by number. Okay? And so you're going to have to go through all 4 million numbers to find the number that's similar to that. Okay, this is all a little bit passé because nowadays you just put the number into Google and scarily, it's a little bit scary, Google will just give you her number. Okay, anyways, the whole story is a little bit outdated anyways. Nowadays nobody gives numbers, you become Facebook friends or something like that. Okay, just want to say, if you watch old movies, you'll see the police department in old movies, they always had what's called a reverse telephone book. What's a reverse telephone book? Those are telephone books that the telephone companies used to make up, which were sorted by number. You gave it in the number, and then it gave you out the name of the person. Okay? Anyways, Google can do both ways. You type in the name, it's going to give you the phone number. You type in the number, it's going to give you the thing. But anyways, so the main point here, the main point I'm trying to show you is there are 2 different ways of solving this. Okay? Each way of solving it is called an algorithm. Okay? An algorithm is a procedure, a way of doing things. Okay, we're going to see a little bit more of that later. An algorithm is a procedure, a way of doing things, and there are 2 possible ways. But you have to do one way, you have to do it depending on what your needs are. Okay? So this is the brute force search algorithm, and this is called the binary search algorithm. Binary for split. Great. Okay? And you have to keep these numbers in mind. You have to realize that this number is usually a lot smaller than that number. Great. Okay. Next. Okay. The next thing is, we see here that it's very important to keep your data sorted, okay? To keep your data in order. So one of the things we want to do is we want to sort We want to sort things. We want to put them in order, okay? And if you work in an office, you like to sort things, you like to keep them in order, etc., etc. But I don't want to talk about keeping things in order. I want to talk about from an unordered to get it into an order. And that's the next thing we're going to deal with. Okay, so here's 16 cards, they're not in order. They're not ordered. I'd like to do two different ways of putting them in order. Okay? The first way is called the selection sort. Okay? It's a very easy sort, and we're going to see how to do it. This way to do it is as follows. You listening? Okay. What I'm going to do is I want to put this in ascending order, going up, starting from the lowest, going down. So what I do is I search through it, finding the smallest number. Okay? And here's the way I do that. I say 34. Is 34 less than 13? No, 13 is less. So here's the smallest number. Okay? 13 is less than 48? Yes. 13 is less than 24? Yes. Yes, 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 yes. 13 is less than 35? Yes. 13 is less than 47? Yes, 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 yes. 13 less than 8? No. 8 is the smallest number. So I put my finger here. This is the smallest number so far. Is 8 less than 46? Yes. Is 8 less than 39? Yes. Okay, so here's the smallest number. Now I take the smallest number and I swap it over there. Hold on. Let's just make this a little bit more interesting. Great. Now this part of the list is already sorted. This is unsorted. Now I go through this list. Ready? Okay? No, I'm sorry. I go through the rest of the list, and what I do is I look for the smallest number of the rest of the list. 47 and 48, what's smaller? 47. 47 and 24, what's smaller? 24. So this is now my smallest element of my list. 24 and 22, what's smaller? Answer, 22. So this is now my smallest element of the list. Now, 22 and 32 is what's smaller? 22. 22 and 33, what's smaller? 22. 22. 22 and 13, what's smaller? Okay, 13. Okay, and then I keep on going. 13 is smaller, 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 13 is smaller. Conclusion, this is the second smallest element of the list, and we put it over there and swap it. Okay, and we keep on doing this over and over. I'm going to look through the rest of the list and see how small it is. Okay, I'd like to keep track of how many questions I ask here. Okay, 48 and 24, what's smaller? Okay, and the answer is 24. 24 and 22, what's smaller? 22. Okay, so I just asked two questions, then I'm going to ask 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, 22 is smaller, and I put this over here. Okay, the next thing smallest is going to be 24. The next smallest, I think, is going to be, I'm going to go through this list, find that 32 is the smallest. I'm going to swap that. The next I'm going to find is 33 is the smallest. I'm going to swap that. The next, I'm going to go through the entire list. I'm going to find 34 is the smallest, and I'm going to swap that. Okay, and we keep on doing it. Okay, I put every single thing in. I'm going to go on. I put in every single thing in order. Question: how many comparisons of little cards did I have to do? Okay, and the answer is as follows. Ready? The answer is as follows. When I did it for the first card, I had to compare. There are 14 cards altogether, but I had to compare 13 of the cards. Okay, I compared 8 to all the other cards. I compared the first card to all the other cards. So I compared 13 different comparisons. The next, I was looking through all the other cards. There are 14 cards. I looked through the 13 cards, and I had to compare those, and it's 12 comparisons. Okay? Then I had to do 11 comparisons, then I did 10 comparisons, then I did etc., etc. Okay? Then 3 comparisons, then 2 comparisons, then 1 comparison. Okay? So I had to do this many comparisons. Okay? Question, what's that equal to? What's 1 plus 2 plus 3 plus 4 plus 13 equal to? Okay? Answer, I don't know, but I have to tell you a cute little story. About 150 years ago, there was a guy named Carl Friedrich Emanuel Gauss. I'm not sure about his first name, but his last name was Gauss. And he later on became the greatest mathematician who ever lived. Okay. But when he was 5 years old, he wasn't behaving properly. Okay. In class, he was jumping around, he had ADHD, he wasn't behaving properly. So the teacher, to keep him busy, she told him, hey you, Gauss, add up the first 10 numbers. Add up the numbers from 1 to 10. Thinking that this would keep him busy for a while. Okay? Anyways, without thinking, or in an instant, Gauss jumped up and he said 55. He just said, the answer is 55. Teacher didn't know that teacher thought he was just kidding or something, so she kicked him out of the office. That night she went home and she added up the numbers. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10, and she got 55. How did he do that? The next day, he again wasn't behaving. So she knew that he was pretty good at numbers, whatever, but she figured she'll give him a tough number. So she went over to him, she said, Gauss, add up all the numbers from 1 to 100. Okay, and without blinking, Gauss gave the answer. He said 5,050. She thought he was kidding. She kicked him out of the classroom. The next day, she comes in. That night she goes home and she adds up all the numbers. It took her a long time. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, all the way till 100. And lo and behold, she got exactly the same number, 5,050. She was in shock. Then she figured like this. Maybe the kid Gauss, he figured out these numbers beforehand because she asked him about 10 and 100. So she's going to try a different number that he doesn't know what the sum is. So the next day she came to class, and again, little Gaussy wasn't behaving well. So she said, Gauss, add up all the numbers from 1 to 376. He jumped up and he gave the answer. I don't know what the answer is, but he gave the answer. Okay? She was blown away. Anyways, that night was their weekend, and she was able to spend the whole weekend to add up all the numbers from 1 to 376, and she saw that he got it exactly right. Okay? So the question is, how did he do it? Okay? And I'd like to show you his trick. But the trick is a very cool trick. It goes like this. We need some more boardroom. It goes like this. Let's say we do 1 plus 2 plus 3 plus 4 plus 5 plus plus 97 plus 98 plus 99 plus 100. Okay? When I add up all the numbers from 1 to 100. Now, the way I would do it, and the way most of you would do it, and the way the teacher would do it is as follows. 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15, plus 6 is 21. And we keep on going until we get to 100. But Gauss knew the following. A plus B is equal to B plus A. Well, we all know that. It doesn't matter how you add things. 5 plus 7 is equal to 7 plus 5. It doesn't matter what order you do things. But Gauss understood the meaning of that. What it means is that when you're adding numbers, it doesn't matter what order you do it. So why do it in the usual order? 1 plus 2 is 3, plus 4 plus 3 is 6, plus 4 is 10. Don't do it in the normal order. Do it because it doesn't matter what order you do it. Do it in a different order. And so he said like this. 1 plus 100 is what? 101. 2 plus 99 is 101. 3 plus 98 is 101. 4 plus 97 is 101. Dot, 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 dot. Keep on doing that. Okay, great. Now, you have 101. You have 101. Okay? How many pairs of numbers do you have like that? Okay? This is a pair. 1 and 100 is a pair. 2 and 99 is a pair. How many pairs of hundreds do you have? How many times are you adding up 101? And the answer is you have 100 numbers altogether. You split them into 2s, okay? You have 50 pairs. Okay? So, if you want to know how much all these numbers are, all you have to do is one multiplication. 101 times 50. 101 times 50 is a very simple number. Well, all you have to do is do this multiplication. 50 times 101 is 5,050. Okay? And that's called Gauss's trick. Gauss knew this when he was a 5-year-old kid. So when she said to him, add up all the numbers from 1 to 100, what he just had to do is 50 times 101. Okay? Let's just do it for another number. Okay? Let's say you went from 1 plus 2 plus 3 plus all the way till 376. Okay, here you do 375, here you do 374. Okay, so you add them like this. 376 plus 1 is 377. 2 plus 375 is 377. 3 plus 374 is 377. So, how many numbers, what would you get when you get all this up? You get 377 each time, and how many pairs do you have? And the answer is, you have 376 divided by 2 pairs. Now, all Gauss has to do is a multiplication and a division. Divide by 2. Not such a hard division. Anyways, Gauss could do that like very quickly. But it's easier to do one multiplication and one division rather than 376 additions. Okay? Great. Okay? Let's say, we're going to do this again and again, over and over. Let's say he has n columns. You want to add n numbers. So you want to add 1 plus 2 plus 3 plus 4 plus n minus 3 plus n minus 2 plus n minus 1 plus n. Okay? So let's see how you do this. 1 plus n is n plus 1. 2 plus n minus 1 is n plus 1. 3 plus n minus 2 is n plus 1. Dot, dot, dot. Okay? Then let's just do it together. You get n plus 1 times how many pairs? N divided by 2. Okay? Let's multiply this out. This becomes n times n is n squared plus n divided by 2. Okay? And we'll see later that that's kind of equal to n squared. Okay? It's kind of equal to n squared. Okay? But the main point is, Gauss, long before there was a computer, realized he was changing the algorithm. Rather than doing all these additions, rather than doing n additions, if you could do one multiplication and one division, you got the whole thing done. Okay, so that was very clever of him. Okay, let's get back. So, why did we bring this up? Because we were talking about the selection sort. Let's just remember what the selection sort is. Selection sort. The selection sort is, we go through all the cards, we choose the minimum. We go through all the rest of the cards, we choose the second minimum. We go through the rest of the cards, we choose the third to the minimum. Keep on doing that. And that would take 13 plus 12 plus 11 plus plus 2 plus 1 operations, okay? Which we can use Gauss's trick to figure out. So let's do that. That's 14 times, because 13 plus 1 is the same as 12 plus 2, that's 14 times, there are 13 cards, so it's 13 divided by 2, so this becomes 7 times 13. 7 times 13 is 70 plus 21 is 91, so that's 91 operations. Okay, then we would have to do 91 operations. Great. Now, if we had n cards, and we wanted to do this, it would be something like this. For n cards, okay, well, you'd have to go through adding up how many times in comparison, and like we said, it's about n squared. We erased it over there. It's about n squared. So the selection sort, how many cards does it take? How many operations does it take? About n squared. Great. Okay, so that's one algorithm that we can do for sorting. I'd like to show you another algorithm, but the other algorithm, I'm not going to go into the nitty-gritty details, but you're responsible to know it. It gets a little bit more complicated. So let me just unsort this for a second, and let me show you how we're going to do it. Okay. The other sort is as follows. What you do is, you have 16 cards here. Split the cards in half. 1, 2, 3, 4, 5, 6, 7, 8. Split the cards in half. Great. Okay. We split the cards in half. Now, what I'm going to do is, I'm going to sort this side, and I'm going to sort this side. Okay? Okay? Now, question, how do I sort this side? Well, I split the cards in half. How do I sort this side? I split the card. Now, what I'm going to do is, I'm going to split these into half, these. I split these and these. Now I'm going to sort this side, and I'm going to sort this side. And we're going to do it. Okay? So let's do this. This becomes, well, how do I sort these? Well, I do it like that. Split them in half. Constantly chop, 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 chop. Okay? You split the cards in half. Okay, great. Now I have 2 cards. Okay, now I have 1 card. Okay, now I want to merge them. Merge them means bring them together. But this is sorted, bring it together, it's like this. Now I'm going to split these in half. Now I want to sort these 2. This is sorted, I'm going to bring it together, make it like that. Okay, great. Now I have these 2 are sorted, these 2 lists are sorted, I want to bring them together. Okay, it's not hard to bring things together. I do it like this. Well, now this is sorted. Let's do the same thing here. It turns out this whole thing is sorted already. Great. Now I want to bring these 2 together. Okay, it's not hard to bring two sorted things. It goes as follows. Basically goes like this. Okay, now this whole list is sorted. Now I'm going to go here, I'm going to quickly sort the right side. Okay, so again, it's chop, 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 bring together, bring together, bring together. So we chop, 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 we bring together, bring together. Okay, this is sorted, this is sorted. Now I'm going to bring them together. And when you bring them together, it's just like that. Done. Okay, chop, chop, chop. This is sorted, bring it together. It's like this. Okay, great. Now, this side is sorted, this side is sorted, and now I'm going to merge them together. Merge means bring them together. So we do it as follows. 8 and 13. Okay. This goes here. This goes here. And pretty much this goes here. It's not so hard to do. Again, we're not getting into the nitty-gritty details of it, but it's very easy to do. The reason why I'm bringing this sort is it's different than the selection sort. It's called the merge sort. Okay, it's another algorithm. And question, how much work is done? And the answer is n times log of n. Okay, n times log of n. So it depends on how many cards you have. But if you have n cards, then it's going to take n times log of n to do that. That's a lot better than doing this. So let's talk about it. Let's say you were hired to sort the Brooklyn telephone book. Let's see how much operations that would take. Okay, so the Brooklyn telephone book has 4 million people, 4 million numbers in it. Okay, so 4 million squared is, that's a tough one. Okay, 4 times 4 is 16. A million times 1,000 is a billion, times 1,000 is a trillion, so that's 16 trillion. Okay. Let's talk about the merge sort for 4 million. So here you have 4 million times the log of 4 million. What's the log of 4 million? We did that in class. What's the log of 4 million? 22. Okay, so this is 4 million times 22 is 88 million. Okay, you would rather do 88 million operations than 16 trillion operations. This will take a typical computer about 3 minutes, probably even less. This would take a typical computer a couple of weeks. So that's a lot worse than that. So you'd rather do merge sort. Merge sort is a little bit more complicated. If you like selection sort is very easy to understand, but this one is a lot quicker. Okay? I just want to show you, before we go any further, that there's a nice example of selection sort in the book. Just give me 1 second. Hold on. On page 103, I show you how selection sort works. You have a bunch of names, words, 3-letter words, okay? You search through them, you find the smallest, you swap it. You search through the rest, you find the smallest, you swap it. You search through the rest, you find the smallest, you swap it, etc., etc. Keep on doing it. Okay? And I show you that it's n log n, and we talk about it. So that's all till page 104. Great. You have to go out? Okay. Okay, great. So we did sorting. Let's just review. We did addition, basic arithmetic, addition and multiplication. We did searching, and we saw 2 different algorithms for searching, the brute force algorithm and the binary search algorithm. And we did sorting. We saw 2 different algorithms for sorting, the selection sort and the merge sort. Great. Now for the interesting part. Okay, this has a little bit of a background, so I'll give you the background. The background is as follows. There was a city in Russia called Königsberg. And the city was a lot like New York City in the sense that it was a city on a river, okay? And there was lots of water here, okay? And there was an island. This was a landmass, this was a landmass, this was a landmass, but there was lots of different islands, and different landmasses were connected, okay? They were connected with 7 bridges. 1, 2, 3, 4, 5, 6, 7. There were 7 bridges in Königsberg. And what people used to do is as follows. On long Sunday afternoons, by the way, the city, when the Soviet Union took over, they changed it to Kaliningrad or something like that. Okay, and they recently changed it back to Königsberg. Okay. The city is also famous because over here is a church. Okay, and in that church, the great philosopher Immanuel Kant was buried. He lived in this city. He never left the city, and he was buried in there. So it's a famous city. I mean, it's not a famous city, but it's an important city. Okay, anyways, let's go on. By the way, in New York City, how many bridges are there? Stop the computer and stop the YouTube thing and ask yourself the following question. How many bridges do you know in New York City? Let's go through it. You have the George Washington Bridge, the Verrazano Bridge, let's do tunnels also. The Lincoln Tunnel with an H. There's the Robert F. Kennedy, there's the Kosciuszko Bridge, etc., etc. You could probably list off about 10. If you go to Google and you type in the number of bridges in New York City, you'll see that there are 2,000, about 2,000 bridges in New York City. So there's a lot of bridges in New York City. Anyways, so let me just get back to here. So in Königsberg, they had the following thing. Okay, the people in the city used to like to take little trips. They would take little trips, and they would try to cross all 7 of the bridges continuously. Okay, cross all the bridges exactly once. So they would start here, let's say, and try to cross every single bridge and come back to here, the same in one little stroke. Okay. My grandmother lived in Williamsburg when she grew up. She said on Saturday afternoons they used to walk across the Williamsburg Bridge and come back on the Manhattan Bridge. Okay, that was the activity for Saturday afternoon. But question: Can you do that? Can you cross all 7 bridges exactly once? Okay, so try it. Let's see. Start here, go here, go here, go here, go here. Uh-oh, you gotta do this bridge. But if you do this bridge, you can't go out because you did these 3 things already. So you can't do that. Okay, so try something else. Go here, then here, then here, then here, then here, then here. And you can't get back here. Again, what you have to do is come back to the original bridge. Anyways, so this was an interesting problem that people used to do. They had a hard time doing it, and I'll show you why in a second. Okay, at some point, I'll just give you back the history about it. At some point, the Tsarina, that's the female Tsar, the Tsarina of Russia decided that she wants to improve Russia, so she went to Germany and she invited one of the great mathematicians in Germany to come to Russia. His name was Euler. Leonard Euler. He was a great mathematician, and she invited him to come to Russia. And while she was there, she asked him about this problem. She told him that some of the citizens in Königsberg are trying to do this, and she'd like him to think about whether it can be done or not. So Euler thought about it for a while, and he decided to, he went through it and he decided like this. So he said like this: you know what, the person could do it, they're walking here, they could go visit the church over here, then come here, then buy ice cream here, and then go here, and then stroll around, etc., etc. We don't care about what they're doing on the landmass. We don't care what they're doing, how they're strolling around, are they going to the church, are they going to ice cream? We don't care. Are they making a barbecue? We don't care. So to make the problem a little bit easier, what he did was he shrunk the 4 landmasses. 1, 2, 3, 4 single points. So he had a point here, and a point here, and a point here. Those are the 4 landmasses. Landmass, 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 and landmass. And then he said, you know what? I don't care how big the bridges are. I don't care if the bridges are made out of wood or they're made out of stone. I don't care what they are. I don't care how long they are. So I'm going to connect them like this. 1 bridge, 2 bridge, 3 bridge, 4 bridge, 5 bridge, 6 bridge, 7 bridge. Okay? And now I ask the following question. So we have the 7 bridges, just like here. And now I can ask the same question about taking a stroll in Königsberg about this little graph. I called it a graph. Okay, this graph. Okay, question. Can I start at any point without picking up my pencil, come around, hit every single edge exactly once, and come back to the original place? That's what he asked. Okay? Again, can I start at any point, any one of the points, travel around, hit every single edge and come back to the original thing. So let's see if we can try to do it, okay? If I were you, I'd try to do it yourself. You ready? So we're going to start here, then we're going to go here, then we're going to go here, then we're going to go there. Okay, now I only have 2 places, 3 places I can go. I can go up, down. Let's try here, then I go here. Bzz, can't go. I will not get to this thing. Okay, so he had a hard time doing this. Okay, so what he did, what was he? The answer for Königsberg is no, it cannot be done. But I'd like to show you more why. Okay, so Königsberg started the field called graph theory. This is a graph, and graphs show up all over. I'll just tell you graphs, where graphs show up. Okay, I'll give you a few examples of graphs. Take out your subway map is a graph. Graphs are made out of dots and arrows between the graphs. So a subway map, if you think about it, the dots are what? The dots are the stations, okay? And the edges between them are trains, okay? And you can talk about the subway map. Take any street map, okay? The dots are the corners, okay? And you can go through the streets. Now, think about New York City. You have one-way streets versus two-way streets, so you might not be able to go between every street. Let me give you some other examples of graphs. Facebook is a giant graph. Okay, the dots are the people, and 2 people are related. There's an edge between 2 people if they're friends. Friends on Facebook. Okay. The World Wide Web. The World Wide Web is a giant graph. Every web page is a dot, and if there's a link from this web page to that web page, then there's an edge between them. Okay, great. Okay, so Euler invented the notion of a graph, and then he asked what the Tsarina asked him. Okay, he said as follows. Given a graph, can you cross every single edge exactly once and come back to the original thing? So he said like this. Here's a typical graph. Okay? Can you cross every single edge and come back to the original thing for this one? Okay. If you think about it long enough, you'll see that you can't. Okay? Okay, let's try this one. We're going to go through a few different examples. How about this? Can you cross every single edge, start at some point, cross every single edge, and come back to the original one? Okay, here you can. Let's just do it. You ready? I'm going to do it with writing. It goes as follows. We'll start here. We'll go like this. We'll go like that. We'll go like this. We'll go like that. We'll go like this. We'll go like that. We'll go like that. We'll go like that. Okay. Can you draw it without picking up your pencil? That's exactly what you're talking about. Can you draw this picture without picking up your pencil? And the answer is yes. So we say as follows. This has an Euler cycle. Okay? It has an Euler cycle. Euler, that's his name. Cycle means start at some place, come back to the original place. Okay? Let's do another one. How about this? Can you draw this picture without picking up your pencil? Okay? Let's just draw something a little bit more confusing. Can you draw this without picking up your pencil? Okay. And the answer is yes, you can. Let's do it. a lot of different ways of doing it. Where did I start? No, I'm sorry, you can't do it. Okay, because I started here, and I'm going to end up there. So there's no Euler cycle. Okay, well, we can ask an easier question. How about what's called an Euler path? An Euler path is I hit every single edge, but I don't start and finish in the same place. I can start someplace and finish in a different place. So this is like taking a path in a forest. You start someplace, you end up another place. An Euler cycle is where you start one place and you finish in the same place. Okay, so let's talk about Euler cycles. This has an Euler path. I finish here, and I go here, and I'm okay. Okay. Does this have an Euler path? Okay. No, this does not have an Euler path, because I have to finish in the same place as I started. Okay. How about this? Does this have an Euler cycle? Okay, and the answer is no, this doesn't. You have to try a lot, but it does have an Euler path. Let me just show you the Euler path. I start here and I finish here. It goes as follows. I started here and I finished there. So it has an Euler path. This has an Euler cycle, it doesn't have an Euler path. This is an Euler cycle, and it does have, this does not have an Euler cycle, but it does have an Euler path. How about this? Euler cycle, Euler path. Okay? If you go through it, you'll see it doesn't have an Euler cycle and it doesn't have an Euler path. Okay? You should try a lot of different examples. Great! What about the original Königsberg problem? Well, let's remember what the original Königsberg problem was. It goes like this. Okay. If you go through it, you'll see it doesn't have an Euler cycle. Oops. Good Lord. And it doesn't have an Euler path. It does not have either. Okay? In the book, I talk about fixing it, not fixing it, but changing this problem, like this. Let's say we added another bridge. Königsberg came into a lot of money, and they added another bridge. Can I then do it? Okay? And you'll see, if you sit there for a few minutes and try it, you'll see it does not have an Euler cycle, but it does have an Euler path. I want to show you. Here's the Euler path. Start here. Oops. Did something wrong. Hold on. Let's do that again. 1, 2, 3, 4, 5, 6, 7. We add another product. Okay, so let's do this. So start here. That's where we started. Here's where we finished. Okay, so this does have an Euler path. Okay. Anyways, so if you're a typical person, every time you see this, you've been doing like this, going around, trying this, trying that, etc., etc. Euler was a great mathematician, and he figured out a trick for this. I'd like to teach you, I taught you Gauss's trick, I'd like to teach you Euler's trick. Euler's trick is as follows. You have to keep the following thing in mind. Let's say you have some point, and you have a few things coming out. 1, 2, 3, 4, 5, 6, 7. You have 7 things coming out. Okay? Now, the main idea is I can't go on any bridge more than once. If I can go on any bridge more than once, then I can do anything. Okay? In other words, if you're going to do a bridge, you can't do it again. If you're going to do an edge, if you're going to cross an edge, you can't do it again. Okay? And so let's just see what would happen. Let's say I start in the city. I start in that dot. Okay? And I go out. So I can't use this bridge again. So this is my starting place. I can't use this bridge again. Okay? Great. And I bounce around to other nodes and things like that. And I come back over here. Okay, great. And I can go out over here. Okay, and I bounce around and I go do other things. And then I come back over here, let's say. And I go out over here. Great. And I come back over here. And I go out over here. Great. But one thing for sure, I can never go back inside there anymore. Because I have an odd number of edges coming out. So if I start in here, I have to end someplace else. Okay? In contrast, let's do it if we have an even number. Let's do it if we have an even number. 1, 2, 3, 4, 5, 6. Okay? We're going to do the same trick. Let's see what we have. Okay? I start here, go like this, bounce around over here, come in here, go out here. I started here. Oops, 1, 2, 3, 4, 5, 6. Okay, gotta do that again. We're a little confused. Don't rush. Okay, let's do that again. 1, 2, 3, 4, 5, 6. Okay. Okay, if I start here, I go here. Let's say I bounce around, I come in here, I go out there, and I come in here, and I go out here. So I won't get stuck. If I have an odd number, I get stuck. Okay, good. Okay, so Euler's trick is as follows. He said as follows. I need some room. He said, you want to know if there's an Euler cycle? You want to know if there's an Euler cycle? Very simple. Look at all the edges. Look at all the dots. See how many edges are coming out of each dot. If there's an even number of edges coming out of every single dot, then it has an Euler cycle. Let's do it. Ready? Okay. Let's look at it. Here was something that had an Euler cycle. Okay. Let's go through it. Let's see. 1, 2 is an even number of things. 1, 2, 1, 2, 3, 4, even. 1, 2, 3, 4, even. 1, 2, 3, 4 is even. 1, 2, 3, 4, even. Even, even. If they're all even, then there's no problem. You can have an Euler cycle. Okay? Because wherever you start, you can always get in and out very easily. As opposed to that, this guy had, let's see, even. There's 1, 2, 3, 4, even. 1, 2, 3, 4, even. 1, 2, 3, 4, 1, 2, 3, 4, even. And this, look at this node. 1, 2, 3. This is odd. 1, 2, 3. This is odd. He said like this, you will not have an Euler cycle here. Okay? But if you have two odds like this, you can have what's called an Euler path. You can start here and finish here. Okay? So let's do it. You can start here, do this, 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 finish here. You could start in the odd place and finish in the odd place. You could also start here and finish here. It doesn't matter. But the main point is the nodes, the dots, with the odd number of things coming out of it, you're not going to be able to, if you start there, you're not going to be able to finish there. If you finish there, you're not going to be able to start there. Okay? So when they're all even, there is an Euler cycle. When all but two are odd, then there's an Euler path. Okay, great. Let's look at this one. Okay, this is even, but notice odd, 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 odd. You have 4 nodes that are odd. There's no way in the world you're going to have an Euler path here, or an Euler cycle, okay, because you have too many odd nodes. Again, if all are even, then you have an Euler cycle. If all but 2 are even, you have an Euler path. If more than 2 are even, you don't have anything. Okay? Now let's go back to this original question. The original question was here. Königsberg bridge problem. Okay, we have 1, 2, 3, 4 nodes. Let's go through the nodes. 1, 2, 3 things coming out of it, odd. 1, 2, 3 things coming out of it, odd. 1, 2, 3, 4, 5, odd. 1, 2, 3, odd. Odd things coming out of it. There are 4 odd nodes. No Euler path, no Euler cycle. In contrast, if we build an extra bridge, look what we have. This is odd, this is even, this is odd, this is even. You have an Euler cycle path, but not an Euler cycle. Okay? So that answers the problem. Okay, great. Okay, so that answers the problem. So, ready? Now let's make it into a computer problem. Okay, if I give you a graph and I ask you, does it have an Euler cycle? Does it have an Euler path? And I promise you on the quiz, on the test, I will give you such a graph and I will ask you such questions. Does it have an Euler cycle? Does it have an Euler path? It's very simple to check. What do you have to do? You simply have to go through each node, count how many edges are coming out of that node. If they're all even, then you have an Euler cycle. If all but 2 are even, then you have an Euler path. If more than 2 are odd, then you have to try it. Then you don't have an Euler cycle and you don't have an Euler path. By the way, there's something I'm missing here. Okay, what am I missing? Question: what happens if there's a graph where all are even except there's one odd vertex? There's one vertex that has an odd number of lines coming out of it. Does it have an Euler cycle or does it have an Euler path? I'm going to leave that for you. Okay? If you're really interested in that, then send me the graph by email, and I will tell you if it has an Euler cycle or an Euler path. Okay, great. So it's a very simple problem to solve, to tell whether or not a graph has an Euler cycle or an Euler path is a very simple thing to do. What do you have to do? You have to go through each vertex, count up on each vertex, and see if it has an Euler, see if they're all, how many odd vertices are there. If they're all even, if there are 0 odd, then there's an Euler cycle. If there are 2 odd, then there's an Euler path. And if there's more than 2 odd, then it doesn't have an Euler cycle and it doesn't have an Euler path, and you're finished. Okay, just a few little things about graphs, because the graphs really show up all over. There's something called the 6 degrees of separation. So I give you a few examples of graphs. They show up all over. For example, computer networks. Okay, you have a bunch of computers. If they're connected by a wire or they're connected by Wi-Fi, then there's an edge in between them. So you can look at those things. Anyways, there's an interesting graph that sociologists talk about, and they say as follows. They say the human race, okay, is what's called 6 degrees separated. That means every single person on planet Earth can know every single other person on planet Earth by 6 degrees. In other words, I might not know some farmer in some province in China, but I know somebody who knows somebody who knows somebody who knows somebody who knows somebody 6 times who does know me. In other words, let's say I know 1,000 people. Well, fine. But how many people do those 1,000 people know 1,000, each one knows 1,000 people, which know 1,000 people, et cetera, et cetera. And so they've calculated that about, between any two people, there are 6 links between them. I have to just tell you of an interesting experiment that was done by National Geographic. I remember seeing it someplace. Okay, what they did was they sent out 50 boxes randomly around the entire country, and around the entire world. In the boxes, they explained to the people they're trying to do this, and they also randomly picked 50 other names of people, and they said, look, for each box, they said, your goal is to try to get this person. And they told him which country he lives in, which city, whatever. Okay? If you know somebody, please take your box and send it to that person to try to get it. Anyways, that person was supposed to take it, okay, and look at the name of the person. Obviously, he's not going to know that other person, but he's going to know somebody who knows somebody who, let's say he's in France. Well, I know somebody who has a French mother-in-law, so I'll send it to him. Okay? And that person's going to send it to that person, and he's going to send it to that person. And each time, National Geographic asks them to write who they are, and National Geographic will reimburse them for all mailing costs, and put down in the paper who they are, and et cetera, et cetera. And if they were the last person, they asked the last person, do me a favor, send this completed box with the completed form into National Geographic. And what National Geographic then did was it went through and interviewed the people and made a movie out of it, a documentary about how we're all so connected. I don't think many of the 50 boxes ended up being successful. Most people just looked at it and said, what the hell is this? Threw it out. Okay, but some did, and I think it was an interesting experiment. So we're all okay, great. So let's just go through what we did today. You ready? We talked about easy computer problems. We talked about addition. We talked about multiplication. We talked about searching. We had 2 different algorithms for searching: brute force algorithm and binary search. We talked about sorting. We had 2 different algorithms for sorting. One was called selection sort, one was called merge sort, okay? And we talked about the Euler cycle and the Euler path problem, and we showed how it's easy to solve it. You just go through every single node and see how to do it. You don't have to try every single possibility, you just have to try every single node. Okay, these problems are very easy problems, and they're called P problems, P for polynomial. Okay? Because notice what they were. They were n squared, they were n times log of n, they were easy, they didn't take a lot of things to do. What we're going to see in next class, which is section 5.2, is we're going to see harder problems, which take a lot more time to do. Okay? So we're going to try that and we're going to get into that. Okay?